So before I continue today's class, where I'm going to talk about random access process, I just wanted to look at one more time on the steps that we see here as part of the initial access when you power on a handset. So anyone having any queries or doubts about how a user equipment ends up getting parameters that are required for doing random access so that it can also get uplink synchronized with the base station. So on these steps, anyone having any queries or any issues? No? So is that everything clear to all of you? So okay, maybe I will then start talking about the identifiers. I guess I shared a couple of links for you to go through. So one of them is on different identifiers your user equipment will get. Can somebody answer me the query that I posted in the Google Classroom? So which one is your mobile number? Can anyone answer it? Vishal, can you answer? So did you get my question?
No, sir, I'm not exactly. You should query.
Hello, sir.
So in the Google Classroom, I
Yeah.
posted a query. I was asking out of IMSI, IMEI, and MSISDN, which one is your mobile number that you'll be sharing with your friend or your relatives? So you didn't go
Not
through the
for
link?
this.
Okay. And Alram, can you able to answer it?
Sir, no, sir, I did not go through them.
Oh, really? So I'm teaching at a faster rate than the rate at which you consume the information, is it? So did anyone go through? Those who are in the list today's
Actually,
attendees.
sir, we were busy with the assignment uh, still now.
But this is also important, right? What I am
Yes,
teaching is not orthogonal to what you do in the assignment, right?
yes, yes, that's correct.
When you're debugging the code or something, these basics also are equally important. And what I was asking is, what is your mobile number? Out of all different identifiers, your mobile phone or your SIM card is getting. That was the question. Okay, I think I didn't post it as a query, is it? I did it. Okay, I posted it as an information, is it? Okay, I
It
think
is
that's
MSISDN, sir.
MSISDN. Okay, you are right, Madhuri. Okay, I got it. Why you didn't go through? Because I didn't ask you as a query that you have to solve a certain time. So you thought you can consume it leisurely. Okay, so let me start today's class. And again, see, if I had to teach all these at this slow rate, so I won't be able to finish everything. But let me see how much I can able to cover in today's class. Now, first of all, each SIM card that you purchase will have something called IMSI number embedded inside the SIM card. Okay, that is called International Mobile Subscriber Identifier, which is something globally unique. As you see on the right hand side, it has three parts. One is the mobile country code and the mobile network code. So this is what your SIB1 is advertising as PLMN list. Okay, so if you recall, you can see it here. SIB1 is advertising PMLN ID, and inside your SIM card, you have your IMSI number. A part of that is PMLN ID or Public Land Mobile Network ID, plus there's something called mobile station identification number. So these together will form your IMSI number. Like we have seen, mobile station identifier number. And if you look at this IMSI number is the one that is stored inside the SIM card. And the proper name nowadays is not the SIM card, even though we use the word SIM card, it should be called the Universal Integrated Circuit Card, which nowadays you see when you have debit or credit cards, including the smart cards, all of them are based on this UIIC card. Only thing is the amount of information that you store inside differs depending on whether you're using it as like door access control, or whether you're using it for your cellular networks, or whether you're using it for banking applications or something. Otherwise, all of them are based on this UICC card, which is nothing but a very tiny computer without any battery that you have to insert into your mobile phone. That way, mobile phone will talk with another computer, which is your SIM card, and start retrieving these details and doing the authentication of the user before you send and receive the data. So this IMSI number is not only stored in the SIM card, it is also stored in the case of 4G network in HSS database. In the case of 5G, it is stored in unified data repository. And important thing is, if you check anywhere, this IMSI number is the one that is supposed to be kept in a secure fashion. When you buy a new SIM card, on the back of the package, you see this IMSI number is written, but you cannot actually find with the user interface that you have in the smartphone what is IMSI number, because it is supposed to be kept as confidential to avoid IMSI related thefts, and where somebody can try to steal your SIM card and those kind of things. So example of that you can see here. This is an example of one IMSI number. So other day I was talking about mobile country code, mobile network code. So then we also have this unique identifier for each SIM card, but that is not your mobile number. Okay. And one other thing that you have to make a note here is in 5G, because now we are also talking about supporting non-3GPP radio access technologies, we have another name that is called Subscription Permanent Identifier, SUPI. So if you are using cellular, SUP is nothing is equal to your IMSI number. Otherwise, if it is non-3GP, there is some other number that is given. Here, okay. And when you are doing any of these transactions like authentication of the user, this IMSI number is the one that never leaves your SIM card. So it is always there inside the SIM card, and over there we use something called TMSI. As the name says, it is temporary mobile subscription identifier. And in the case of 5G, it is called subscription concealment identifier. I think it is called, I think there are many acronyms, again, don't worry. So the point I want to try to say here is, because this information is supposed to be kept in confidential manner, mobile phone is given these temporary identifiers. So by exchanging this rather than sending the actual IMSI number, we can able to make sure that nobody can able to put a tap on what somebody is doing and where the user is visiting. So this TMSI and this concealment identifier, these are the ones that are regularly changed. I think it should be ID, I think. I think it is called SUCI, yeah. Subscription Concealment Identifier. So the idea is to make sure that nobody can able to put a tap on what you are doing in the cellular network. Okay, and this is the one that is your mobile number. So it is called mobile station ISDN number. Okay, so again, it has three components. So this is the country code, the first one. Okay, I don't spend too much time on this, but if you look at, for example, in the case of India, it is 91. So then we have something called national destination code. So other day I was showing you these things. And then we have this subscriber number. So this is in fact the unique one per user. And the national destination code is one, like if you look at the example that I'm showing it here, 94949 is the national destination code that is assigned to BSNL in AP and Telangana circuit. So like that, as per national numbering scheme, so these are distributed across different operators, and as the demand increases for more and more SIM cards and mobile numbers, you can see that more and more of these are allocated by devotee so that operator can start providing the services. One thing that is important in the entire context here is the mapping between IMSI number and MSISDN number. The mapping between these two could be either 1:1 or 1:many. So what is the meaning of that? A given SIM card has one IMSI number. That is what's stored inside the SIM card. What operators do is in their core network, in this case, you can talk about UDR, or in the case of HSS, they maintain this MS ISDN number. Even though you say that it is your mobile number, so this is not stored in SIM card, okay? What is stored in the SIM card is only the IMSI number, okay, not MS ISDN number. What happens is when you make any outgoing call, so this TMSI, which is temporarily assigned for a given IMSI number, goes over the network to the core network, like let's say in this case, switching center. The switching center is the one that looks at the HSS or UDR database and finds what is the mapping between IMSI number and MSIDN number. And if you are having this caller ID service, the receiver's mobile phone starts showing this calling party's mobile number, because the originating network's core network will do the IMSI and MSIDN number, and for each outgoing call, it is MSIDN number is the one that is actually transported to the receiver's network. That way your smartphone or your mobile phone can start displaying if you have the caller ID service enabled in your phone. So is it clear to all of you how we do this mapping between IMSI number and MSISDN number? Typically it is 1:1, but you might have seen nowadays when you buy a smartphone which supports only, let's say, nano SIM. So what you have to do is you have to go to your operator and ask them to give new SIM card. So as I was mentioning, each SIM card comes with a unique IMSI number. So initially we have SIM card 1. So it has IMSI 1. It is mapped to your mobile number. When you get a new SIM card, so what happens? In this case, it is a SIM 2. So it has its own unique IMSI number. So now IMSI 2, but this is mapped to the same mobile number of yours. So you might have seen whenever you are buying or basically replacing old SIM with new SIM or a same mobile number, even if you are switching from one operator to other operator. So this is the kind of thing done. The mapping between IMSI and mobile number of yours, that is MSISDN number in the operator's core network. And other point here is 1:n. So it is possible to give several MSISDN numbers mapped to one IMSI number as well. But in practice, that is not used, even though specifications allow 1:n mapping between IMSI number and MSISDN number. We can look at this document to understand what is our numbering system and how different operators are allocated these national destination codes and etc. Okay, so let me get started with the today's class before talking about the random access process. So let me show you the state diagram or the state machine that is maintained at user equipment during its course of operation in the network. To start with, like in the previous illustration, you switch on your mobile phone, then it enters into something called RRC idle state. So initially when you switch on, your mobile phone is in a state called RRC idle. So when it is in RRC idle, it does the process of attaching to the network where it is establishing a radio link with base station. So that is what attach/RRC connect. Then you say that your mobile phone is in RRC connected state. So for you to send and receive the data, for transmitting and receiving the data, so your mobile phone has to be there in RRC connected state. In RRC idle and RRC inactive state, it cannot send user data. And again, it cannot receive user data. So it is RRC connected state is the important state. So while it is in RRC connected state, yes, we can also have the process of detaching. Then you come back to RRC idle when you are getting out of the network or when you are powering off the mobile phone. And all these cases, you'll come back to RRC idle. Or when your mobile phone is not having any activity for a prolonged amount of the time, to save the battery power, you switch from RRC connected to RRC idle. The difference between connected and idle is in the ideal state, you don't have to continuously monitor all different transport channels that are out there to be able to decode various broadcast and control information. But when you're in the connected state, because you are transmitting and receiving the data, you expect to be decoding all different signals. In that case, you are actually spending more energy when you're in RRC connected state. So that's the reason why we have some thresholds where if the mobile phone is not having any activity for a certain amount of the time, it comes back to RRC idle state. Again, there is also another event that can trigger you moving from connected to idle. That is connection failure. That means you are in RRC connected state, but let's say you are moving in a high-speed car. And yes, you are in the coverage area of a base station, but because of the way the channel quality fluctuates and you are unable to really send or receive the data. So if you don't able to successfully transmit or receive data for a certain amount of the time, your mobile phone switches from RRC connected to RRC idle, and again it has to restart the entire process of going back to RRC connected by doing something called uplink synchronization again. So these are the states, the RRC idle and RRC connected at mobile phone, and even the base station also maintains for each mobile phone what is the current state, like either it is RRC idle or RRC connected, so that we have these states for each user maintained at the user equipment side and also at the base station side. But in the case of 5G, now we have one more state that has been introduced to further reduce the energy consumption at the handset sides. That is called RRC inactive. So to a greater extent, RRC inactive is like what we have in the case of RRC idle, where you don't have to monitor all the different transport channels. When you're in the RRC connected, again, rather than going to RRC idle, you go into RRC suspend state. And whenever you have any data transmission to send, then you come back to RRC connected. And if there's any connection failure, again, you have to go back to idle state and redo the entire process of doing the attachment with the network. Why we have this RRC inactive state is nowadays, thanks to smartphones, the mobile phone end up going between these two states quite often. Even when you have any WhatsApp notification or when you wanted to send a small message, you have to end up going from RRC idle to RRC connected. Then you transmit the small data or you receive SMS or whatever it is you are supposed to be receiving. After that, then again you end up coming back to RRC idle. The transitioning between RRC connected and idle involve a lot of signaling overhead. So to reduce the signaling overhead, this particular state has been introduced, which is called RRC inactive. The idea behind RRC inactive and RRC idle is when you are in the inactive state, it is quite faster for you to come back to the RRC connected. When I say quite faster, in the sense that the signaling messages that you exchange to go back to RRC connected are much lesser compared to the signaling messages that you have to exchange to go back from idle to a connected state. Because we are reducing the signaling messages, the RRC inactive to RRC connected will happen quite faster compared to moving from idle to connected state. And also you can see a couple of other state machines at the bottom in the figure. We have something called registration management state maintained at the user equipment and also at the base station for each user. Initially, your mobile phone is in the state called registration management deregistered. After network has accepted the registration, when I say registration means you getting successfully authenticated by the core network so that you can able to send and receive the data. That is called RRC registration process. After you successfully complete that process, yes, you move from RRC deregistered to not RRC, RM deregistered to RM registered. That is the case. And if there's any problem with the registration, then you come back to RM deregistered. Then we have another state maintained again at the user and also in the network side is connection management idle and connection management connected. CM stands for connection management here, where when it is in CM idle, when it is completing all these access network, that means the RAN related connection signaling messages, and when it is initiating the first NAS message in terms of doing the authentication and registration of the network, then you say that you are moving from CM idle to CM connected. And when you finish everything, when you release the thing, you come back from CM connected to CM idle. So like that, we maintain these states not only at the user equipment side and also at the base station and also at AMF and other entities in the core network, so that we can keep track of what is happening at the user and appropriately we can see the state of the user and able to send and receive the data. Again, what I'm showing is at very, very abstract level. This itself could run into multiple classes if you have to really go and deep about how the RRC layer works. As the here RRC stands for, I forgot to say, the radio resource control. It is the control plane layer that you have in the protocol stack at both the user side and also at the base station. It is responsible for taking care of all the decisions in terms of putting the user into the network, doing the authentication and doing the handover. So it is like kind of a brain of the your mobile phone in terms of doing all this activity. Okay, so finally we'll look at random access. And if you recall, so after decoding this SS block, so what did I say about UV status in terms of synchronization point of view? After UV decodes this SS block, so what did we say? Or what did you remember me saying the state of the UV in terms of synchronization with the network?
It is synchronized on the basis of time and symbol, that frequency thing.
Now, is that only time and frequency, or is it more than that? I'm only
Symbol
talking.
level,
Yes.
symbol level synchronization and frequency level synchronization.
Yeah, symbol correct. Frequency is correct, but there is also one more thing that is very important. I say I'm not see symbol. Okay. Oops, what happened? I also mentioned that we have something called off frame bit in MIB, which tells whether the SS block is in the first 5 millisecond of a frame or in the second 5 millisecond of a frame. So do you remember me discussing this point?
Yes, sir. It will also give the boundaries of frame.
Frame means you know what is the starting of each and every frame. So like frame number n, this is frame number n plus 1. So you can know when a given frame is starting and when a given frame is ending. So the length of each frame is 10 milliseconds. So that way you have synchronized with the base station in downlink and you can be ready to listen to whatever the base station is transmitting by keeping your radio awake in whatever the time slots in all these different frames. That way you are synchronized with the base station in downlink. Then we do this initial access or the random access RACH for you getting synchronized in uplink. So that's what I'm going to discuss in today's class. So random access is used by user equipment for connection setup with the network and also for doing synchronized with the base station in uplink. Okay. So not only connecting with the network so that you can able to transmit the data in uplink, you also want to make sure that you have this uplink timing correctly so that whenever you transmit, you are not going to end up interfering with other user transmission in uplink so that multiple users can use shared resource without leading to collisions. So that is the meaning of this random access. We use random access in variety of cases, but in this particular class, I will talk about this mostly in the context of initial random access. When I say initial random access, when a mobile is entering into the coverage of a network or when you power on mobile phone, after you synchronized with the base station in downlink by listening to SS block, you do this random access procedure so that you can also synchronize with the base station in uplink so that you can transmit data in uplink. So that is the thing, but we also do it in multiple cases. The first one you can see is the initial access, where you are establishing a radio link with the base station and you are getting this identifier. I also shared another document or couple of links explaining various identifiers your user equipment is going to get during the course of all these different activities. Here CRNTA stands for Cell Radio Network Temporary Identifier. Okay, so that it can able to send and receive the data and messages. So where the mobile phone moves from either RRC idle or inactive state to RRC connected state after doing this random access process. The second one is re-establishing the link after radio link failure. This is the case I was talking about. Already you have the radio link. Already you are synchronized with the base station uplink, but due to various reasons, your transmissions are not going. Then you have to redo the process. Again, other cases when the user is idle for a prolonged period of the time, then could be the case that when the user is idle, that means when you are not using your mobile phone and you are not getting any notifications or etc. or whatever the reasons for some time, your mobile phone end up moving to inactive or idle state. But then it wants to really transmit anything again in uplink, then it has to make sure that it has uplink time synchronization correctly. So for that, it has to do uplink synchronization again so that it can transmit without leading to collision with others transmission in uplink. Other one is demanding other SIBs from the network. So if you recall, I was talking about only MIB and SIB1 are the one that are broadcasted periodically, whereas the rest of them are optional and can be broadcasted or uh, sent in unicast mode on demand. In that case, if the user equipment is interested in knowing other things, then it has to do random access process and ask for these SIBs. And this is another major important scenario where we also do the random access when you are moving from one base station to other base station as part of the handover process. So when you are trying to connect with another base station, what happens is you are not synchronized with other base station in uplink. For that reason, you have to again do random access process so that you can get synchronized with the new base station in uplink. So in the following class, next week, I will talk about handover. Then you'll see how we are going to use random access in the context of handovers. And other case is in the case where your user equipment wants to send some data in uplink. But unfortunately, the base station has not given any scheduling request. Scheduling request here stands, it is also called SR. Oops. So if the handset is not given any scheduling request, okay, then it has to first make a request to the base station that it wants to send some data in uplink. In that case, it has to again do the random access. So that way, these are all different cases where handset is doing the random access process, which is a four-way handshake between user equipment and the network. So this slide is showing the things in the context of eNode V, that is 4G, but the same call flow or the message flow is valid even in the case of 5G as well. So this is called something called contention-based random access, CBRA, contention-based random access. So this is the only place in cellular networks we have the chance of having collisions and contentions. I will talk about how we can resolve as we go forward in the lecture. But let us look at the slide to understand at the high level what are the things that are happening as part of CBRA. So look at first. So we have user equipment which you have powered on, and it has synchronized in downlink with the base station by doing cell search, basically by listening to SS block. That's what I was describing earlier. Already have synchronized in downlink with the base station. So then the handset has to do this four-way handshake with the base station as part of CBRA, where there are four different messages that get exchanged. These are RRC messages. Basically, these are like messages that are exchanged by having the trigger from the RRC layer. Where if you see these four messages can be further divided into two parts or two major divisions. The first one is step one, where the handset is sending a random access preamble, basically a code sequence it is transmitting in uplink. That is the step one. And as a response to this preamble, the base station is giving random access response. So this response includes something called timing advance. The response from the base station includes the timing advance. So by listening to random access response, handset will do uplink synchronization with the network. So I don't know whether you are able to follow it up or not. So even though it looks a bit complicated, so the process of getting uplink synchronization is very simple. So I was also describing in one of the previous classes. It is like, for example, let's say you are commuting from city to the campus, and let's say you have, take this case where So this is our campus and this is your home. And let's assume that you have some meeting at 4 p.m. and you started at 4 p.m. because you have synchronized with only in downlink. That is the case I'm talking about. So you started at home exactly at 4 o'clock and it will take certain amount of the time to reach the campus. So this is this one. Let's say this is equal to 10 minutes. So by the time you reach and start entering the meeting room, the organizer of the meeting room knows that you are late by 10 minutes. So what the meeting organizers will tell you?
To come
Come
earlier.
by 3:50 for the next meeting.
Come, start 10
Come by-
minutes earlier than the scheduled time of the meeting, right? Next time, whenever you are coming for a meeting, from your current location, you have to start 10 minutes before the meeting scheduled time. So that is called timing advance. That means at what time in advance you have to start your transmission in uplink so that your transmission will reach the base station in the time slot that is assigned for you. So that you will be end up reaching in the slot that was assigned for you without causing interference with other slots that are assigned for them. So is this clear or you want me to clarify further? So, but this is exactly what is happening. And by knowing this timing advance, in this case it is 10 minutes or okay, MS I wrote, it should be MTS. So by knowing that, okay, your timing advance is 10 minutes, you are already synchronized with the base station in uplink. So what I mean by that is, take this example. Okay, I should not be drawing like this. Yeah, let me draw horizontally. So this is at UV side and this is at the base station side. Let's assume that okay, and this is the time, okay, t equal to t1. So I'm just drawing for the sake of illustrating. This may not be exactly how we do in 4G and 5G. So let's assume that these are different slots. I'm just talking in a generic sense. Slot 10, slot 11, slot 12. Same thing. Slot 12. So here I'm talking about uplink. Uplink means so the user equipment is transmitting and base station is listening. So this is the case that I'm talking about. So in this case, what happens is already your user equipment is synchronized in the downlink. In the downlink, it has synchronized. How do you know that it has downlink? It has synchronized because if you look at these two are exactly the same. That means the frame boundaries. If you recall, I was talking about by knowing off-frame bit, you have the things at the frame level. So by having the synchronization in the downlink, so the slot starting times at the handset side and at the base station side are exactly the same. Similarly, in the case of ending of each and every slot. This could be even talked about in the case of subframe or even in the case of frame. So this is the case. But now what could be the issue here is if this user is, let's say, very close to the base station, then if he's transmitting, the transmission from this will end up coming more or less within the slot. No problem, because we have this guard period, the cyclic prefix and guard periods. So they will ensure that even if there is like a few microseconds delay here and there, so they're within the slot that is assigned for the user. So in this example I'm talking about is slot 10 is assigned UV. Okay. And take this case where slot 11 is assigned to UVB, which is far away. So he is transmitting here and he is finishing the transmission here. So can somebody tell me, if I had to draw the reception of data at the base station when user equipment B is transmitting in slot 11, how it will look like in the bottom timing diagram? Is it clear, or what I'm talking about? Are you guys not able to follow me? Can somebody confirm me?
Okay, sir.
No, I asked a question. What is the answer? So did you understand what is my query?
No, sir. Actually,
So what I'm asking is, when user B is transmitting in slot number 11, when the transmissions of user B will reach base station. So this is the frame or the timing. Basically, this is the time axis. Okay. So what time do you think it will reach? So my question, okay, the choices are this one. So it will reach here. That is one choice. So it will reach here. Or I could draw one more. So I'm using black color. It could be reaching here. So which of these three? I'm using three colors, green, red, and black, to represent the starting and ending time of the transmissions from user B reaching at the base station when user B is transmitting slot number 11.
sir, I think it was the black one because UVB is far away from UVA and UVA is getting it then and there. So
Yeah, so that could be one answer, but definitely it is not red region.
yes, of course, yes.
So why I'm saying so? Because user is far away and the propagation delay could be even sometimes 50 microseconds or even 100 microseconds. So because of that, there is a delay at which base station start receiving from the starting of the slot 11. So what has to be done so that we'll be getting the transmission of the user B in the, okay, maybe, oops, 1 second. So I want to make sure that the transmissions of the thing will be exactly coming like this. I want to ensure that. I want to ensure that when user B is transmitting, it will exactly fit inside slot 11. And assume that my propagation delay is 50 microseconds. So what has to be
Then
done?
we have to start sometime before, like let's say 50 millisecond microseconds ahead of time.
So in other words, what you are trying to say is UVB as to start at t equal to S11 minus 50 microseconds. Right?
Yes, sir. Yes.
Otherwise, what will happen? If he is not following that, let's assume that the slot 12, okay, this is given to B, okay, and this is given to A, and A is close. Okay, so what will happen if you don't follow that?
It will collide with A's transmissions.
So because these are the A transmission, okay, and the black color is representing, or the black or even the green color is representing B's transmission. So in other words, neither A nor B's transmission will be successfully overheard and decoded by the base station. Do you agree with me or not? I'm saying that neither A's data nor B's data will be successfully decoded by the base station if you don't do the
Yes.
timing advance of 50 microsecond for user equipment B. So
Sir, how do we calculate this propagation delay then? Like for every UE has to calculate it, right? To perfectly send it in a slot.
so it is exactly like the example that trying to illustrate here. Look at this cartoon that I'm showing on the right hand side. What did I say?
The first time we missed the target, and then the base station say that you are late by this time, and
Yes,
then it readjusts.
exactly. So
Okay.
that is called RACH. So in the RACH procedure, we give a kind of a free hand for user equipment to start transmitting in a relaxed manner. And base station is kind of patient enough to be able to accommodate them, even though they are coming a bit late or bit early or whatever it is. And when the transmission receives, the base station can calculate what is the propagation delay. So do you agree with me or not? Whenever I hear anything from you, if you are, let's say, 2 kilometers from the base station, if I'm the base station and I'm getting something from you, because both of us already synchronized in the downlink and I know which slot I'm allowing you to transmit, if I look at the starting time at which the first symbol from yourself is reaching me, so that will give me the propagation delay that is there between me and yourself, right? So this is what is being accomplished at the end of step 2. So where in the step 1, user equipment is sending a random preamble to the base station. Then the base station will understand what is the time difference. Basically, it can calculate the propagation delay because both of them are already synchronized in the downlink. So the difference in the time at which the clock for that particular slot is starting versus the time at which the first symbol of that particular random access preamble is received is nothing but my propagation delay. Then in the step 2, base station is informing to the user that, okay, this is your timing advance. So you set your clock by this much amount of the time. You tune, like basically you are preponing or making it like that. So that is called adjusting your clock for uplink synchronization. So after this step 2, your base station and your handset are synchronized not only in downlink, but they are also synchronized with each other in uplink. Now, in step 3, the handset can start transmitting just like it is already connected with the network because it knows the timing and it can transmit again, as I was mentioning, by that delta time in advance in the slot that is assigned, it will transmit. Now, what is being conveyed here is what varies depending on whether we are talking about this purpose, this purpose, this purpose, this purpose, or this purpose. Depending on for what purpose we are using the random access procedure, the messages that you carry inside step 3 and step 4 vary. And today's class will talk about RRC connection request and RRC connection setup messages which are exchanged between handset and the base station to be able to complete establishing a radio link with the base station. So as I'm telling again, so this process is there not only in 5G, it is also there in 4G. That's why you see in this slide E node B rather than G node B, but it is the same process at the high level. And we calling this process as contention based random access because in the step 1, so what we do is something called random access, where different user equipment who wants to get synchronized in uplink, they can randomly select one of the available preambles and start transmitting. In the unfortunate situation of two such users selecting same preamble in the same random access opportunity, they end up getting collided. We have to do this contention resolution that you do as part of the step 4 or the message 4. That's why we call it as contention based random access. So this is the summary of what I wanted to talk in the following slides. If you just try to follow me in this slide, then I think the rest of the class you can able to easily understand what I'm describing. The first step is handset sending a preamble on RACH, that is physical random access channel. Base station will calculate the timing advance, and as part of the random access response, it is giving the timing advance, and also it is giving the preamble ID. Each preamble contains something called random access preamble identifier. It is called rapid. Okay, so so when I say preamble, I'm talking about rapid being kept here, so that different user equipment who are transmitting different preambles can check what is the rapid that is coming as part of random access response. If it is matching with their rapid ID, then they comes to know that response is for them, not for somebody else. Then accordingly, they can use the timing advance or synchronizing in uplink. So then look at what else is being carried inside random access response. There are two other parameters that are being shown. One is that uplink grant. So uplink grant is important because you are letting user equipment to transmit message 3 in uplink. Basically, message 3 is like RRC connection request message. For user equipment to transmit message 3, user equipment should be allocated some uplink grant so that it can transmit message 3 without any collision, unlike message 1 which has to go over the RACH channel. So in which time frequency resources your handset can transmit in uplink is conveyed as part of the uplink grant. Then we have something called a temporary CRNTA, which is allocated by the base station and given to the handset. So this helps in the extreme case where the message 3, which is transmitted by the user equipment, let's say for whatever the reason, the base station has not received message 3. Okay, so in that case, what has to be happening is the base station will ask the handset will transmit message 3 by allocating another uplink grant. So the way it allocates the uplink grant is in PDCCH. So when it is allocating uplink, one more uplink grant because of the failure of the message 3, so the PDCH contains this TCRNTA message. The reason why this has to be different, I will explain maybe in the following thing, but that is the main purpose. We use this temporary CRNTA. So then we have this message 3 where you send a connection request message. Then we have this collision or contention resolution that is done as part of the message 4, where in the message 4 we uniquely transmit an identifier ID of one of the QVs. So I will come back and explain how message 4 is the one that is helping in resolving contentions and letting one of them win the RACH process, if at all that is possible. In the extreme case, all the devices which are using the same preamble, they have to redo the entire process. So before I talk further, so let's look at the high level, how we configure this RACH channel. the physical random access channel. So what you see is the RACH resource periodicity. So in this example, what you're seeing is in a RACH period. So it is being shown like we have 3 RACH slots. So this is one, so this is second one, and this is the third one. So that's what being shown here. So I have 3 RACH slot. Again, you all know, right? Our RACH slot is nothing but 14 symbols. Each slot is 14 symbols. So in the case of numerology 0, it is 1 millisecond, and it is 1, it is 0.5. So that way the slot length in time domain reduces as you go to higher numerologies. So this example is showing you have 3 RACH slot inside a RACH period. But if you look at one of the such slot and open up and peek inside it, you can see it has in time domain, again, I was mentioning there are 14 symbols, like, or maybe I can show like something like symbol 0 to 13. And in the frequency domain, so depending on whether you're in FR1 or FR2, the number of resource blocks, the value of M changes, and M equal to 12 in case of FR2. In the case of FR2, basically we use 12 resource blocks per each RACH slot. But in this example, what I'm showing is we can have K, which is another parameter where K can be greater than or equal to 1. And it is less than or equal to 8. So basically it is kind of telling that I can have, maybe I will try to show here. What I'm trying to show is if I take any slot, so this is my slot, and if I to draw, this is my RACH occasion. It is called RACH occasion. Okay, so let's call it as RACH occasion 1. But I can have not only one RACH occasion in the frequency domain, I can have multiple RACH occasions where each of them, in the case of FR2, I am saying these are 12 RBs. So this is another 12 RBs. So this is my RACH occasion 2. And I can take one more. So like that, I can have maximum up to 8 RACH occasions. So basically, this is 1, 2, dot, dot, dot. 8. So what is the significance of this is we can let okay, in other words, what I want to say here is in a given slot, so this slot, I have 8 RACH occasions. So basically it means that it is possible for different users to use these different RACH occasions and transmit the preamble. So the preamble can be transmitted in any of these RACH occasions. It is possible where multiple users can use the same RACH occasion, or that is also possible. And it not only this case, as you go to higher numerologies, we can also have a given slot further divided into multiple RACH occasions. So this, if I come back and show you another example, so now it will look like is, maybe I'll draw a simple example. So this is one slot. Zero, 1, 2, and 3. This is symbol 0 to symbol 13. And these are 12 RBs. These are another 12 RBs. So this is also possible, where I can split a slot into multiple RACH occasions in frequency domain and also in the time domain. So by doing that, we can let multiple RACH occasions available in a given slot, which could be used by any of the user who wanted to do random access in uplink. So that is what being discussed here, where in the frequency domain, we can have the K, that the value of the K could be equal to 8. And in the time domain, we can have 7 RACH occasions per slot. So time domain, okay, maybe here I will showing you 2 here in the time domain. Here I'm showing 2, but it can go up to 7 as well in the time domain. And in the frequency domain, we can have up to 8. These are all within a slot.
Sir, how within a slot can we accommodate 7 RACH occasions? Like
Okay.
one slot is 14 symbols, right?
Yes, yes. One slot is 14. Okay, wait, not here. Okay. Yes, one slot is 14 symbol. Yes, you are right. So what is the meaning of here is, look at here. Okay, wait, just I will explain you quickly. So in this case, what is the meaning of this is 7 symbols are given RO1 and the remaining 7 symbols are given to RO0.
Okay, got it. Yeah. So if we divide it into 7 RACH things, then 2 symbols per arrow.
Exactly. In the extreme case, if you stretch too long and we just end up giving only 2 symbols in a given slot, that way we can have 7 RACH occasions in a given slot in time domain. But okay, I have not explained what is symbol length, what is the preamble length. So we have 2 kinds of preambles, short and long one. And short one is I think 139. So all the thing of splitting is possible in the case of short preambles only. Okay, I will just hold on. I will show you in the following slides how the split is really happening. Okay, so this is an example of an operator configuring some of the slots in uplink for user equipment doing uplink synchronization by doing the RACH procedure. So this is a kind of pure overhead, but without synchronization, we cannot transmit anything uplink. So that way, it is a kind of a mandatory overhead that you have to face. So this is the kind of thing showing how you actually take preamble and do mapping of the preamble into this time frequency resource grid. So what you see is the preamble, like let's assume that the length of this is 139. So P0 to PL. So then you do the DFT transfer.
139 bits.
What is it? Yeah, these are bits. Yes.
139 bits. Okay.
Yes.
Okay.
Yes. Yeah, these are 139 bits. Yes. Then you do again BPSK. Then 1 bit becomes 1 symbol. And look at what else you are doing it interestingly. You are repeating each the code sequence or the preamble sequence n number of times. Then you are adding the cyclic prefix. And after cyclic prefix, yes, you map into the time frequency resource grid where the cyclic prefix is going here. And the n repeated symbol, like in the simplest case, you can assume that you are not repeating anything. When you are not repeating anything, what happens? All these slots that you see in this grid are available to carry these 139 symbols, which are equal to 139 bits. But when you are repeating and when you say n equal to 2, then what you have to do? Like then you say that, okay, these are all to carry the sequence A, and these are used to carry sequence A, but it is a copy of the same sequence again. So what we are trying to do here is we'll be sending same code sequence, which is called a preamble here, multiple times within the RACH slot. So the number of repetitions varies depending on the preamble format. Like if you take the preamble format 0, you do repetition of only once. That means n equal to 1. But if you are using the preamble format 1, then you are doing the repetition 2 times. And when you are taking the format 3 preamble format, we are using the numerology 1.25 kilohertz in the frequency domain, unlike using 15 kilohertz, 13, 60, 120, and 240. We are using very, very small subcarrier spacing here. And we are doing 4 repetitions in the frequency domain. And together these two will tell you the length of RACH slot. And these are all, for the example that I'm showing here, these are all the long preambles. Long preambles contains, okay, I have to just check. I think it is somewhere it is given down the line. Okay, it is 839. Okay, okay, those are 39s. Okay, correct. Yeah. Yeah. These are 839 bits. In the case of long preamble, it is not 139 bits, it is 839 bits. So in that case, we look at the case where we are repeating these 839 bits one time, or we are repeating these 839 bits 2 times, and even the 4th time in the resource grid that you see it here, which is inside one RACH occasion.
Sir, can this entire 139 bits be transferred in one RACH occasion, or we have
Yes,
to
yes,
use multiple?
yes. Like if you come back here and look at here, so
Then sir, we have to give more number of subcarriers, right?
that's why we are giving 12 resource block, right? It is basically 12 into 12, 144 subcarriers we are giving, right?
Yes, yes.
Yeah, you are right. Actually, we are giving more in the frequency. These are not the subcarriers. Frequency domain, what I am showing here is the 12 resource block that I am giving. Okay. And only in the case of short preambles, we have the case of where having more than one RACH occasion in the time domain. Otherwise, we have only one RACH occasion in time domain for long preambles. And also, if you see here, one more thing that is happening interestingly is the length of the RACH slot. This is if you take numerology 0, where slot equal to 1 millisecond. In this case, if you look at for this one and this one, look at what is happening. The cyclic prefix length and the preamble length are actually exceeding the RACH slot length. So what is being shown in the standard is what is the starting, like all these things that I have done here. So this is the starting of the RACH. So it may finish within one, like in the case of, let's say, the preamble format 0, it will finish within it. But if you take preamble format, like as I was mentioning here, so it is taking almost, it is actually going till here. So it is up to the scheduler to make sure that the following slot is not assigned for any user as part of the physical uplink shared channel. Because scheduler already knows that if you are using the preamble format 1 and 2, the slot, RACH slot, extend beyond the boundary of 1 millisecond in the case of numerology 0. So that way it is left up to the scheduling algorithm to make sure that the following ones are not given. And depending on the repetitions, you can see all these variations. Okay, I think I have one figure. Maybe it will help you to better understand. Where is that? Okay, I think this is the one. Yeah. Yeah. So whatever I was talking about is mentioned, like the formats are 0, 1, 2, 3. This is in the case of long preamble. Okay, where the preamble length is 839 bits. And it is talking about the length of the cyclic prefix and the length of the sequences. Like maybe look at here. Okay. Are you guys able to see this part? The picture?
Yes.
So here you can see this is a one slot of 1 millisecond. Inside I have cyclic prefix, which is taking 100 microseconds. Then I have T sequence. Basically, this is where my preamble is kept. The 839 bits are kept. So they are occupying 800 microseconds. Then I have the guard period, which is again taking 96 microseconds. Together, everything is fitting inside one slot. So this is what I was trying to show here. So in this example, if we take format 0, together it is less than 1 millisecond. Everything I can pack inside one RACH slot. But look at preamble format 1. So can you, from the figure, what you can say? In the case of preamble format 1, what you see and how it is different from the previous one?
Slot length is 3 millisecond now.
It is RACH is actually taking 3 milliseconds. That is important. Okay.
Yes.
And look at the colors. And what by looking at these colors you can say? Compared to the previous one, look at TCP, T sequence, and guard period. So what happening to all this as you go to preamble format 0 to preamble format 1?
All of them increased in time.
Exactly. And T sequence, what do you observe for T sequence?
It is twice now.
Yeah. So now tell me which occasion or when, in which scenario you decide to use first preamble format versus the second preamble format. So you are a handset, okay? You have decided to use one of the preamble. Okay, now you have two choices. I will send my preamble sequence of 839 bit only once, where the entire thing will fit in 1 millisecond, or I will use larger cyclic prefix and also use larger guard period, and I will repeat the sequences 2 times in the time domain and in the frequency domain and send it. So, okay, ignoring other cases, if I look at in terms of the base station, out of these two cases, in which case we expect the base station having more ability or the more success in actually successfully decoding the preamble sequence?
Sir, in lower numerologies, like in
No,
0
I'm
or
not
1.
talking for any given numerology. I'm not talking about
Okay,
numerologies.
okay.
Take any numerology. So what I'm saying is I have a user who is at, let's say, at 100 meters or let's say 1 kilometer from the base station. I can give either the first preamble format for the user to send the RACH message, or I can use the preamble format 1, where I will be repeating the sequence 2 times and send my preamble message to the base station. What I'm saying is, if you come back here, so I'm talking about this case here. So you are sending a preamble, right? So either should we use the format, format 0 or format 1? So this is what I'm asking. The user
Format one, sir.
So no, what I'm asking is even more, the more right way of asking is, okay. Who is this answering?
Vishal.
Okay, Vishal. So you are saying that when you use format 1, the base station has more success of successfully receiving the preamble. That's what you are trying to say?
Yes, sir.
Because
Because there are more longer, like duplicate packets. So
basically you are sending the same message 2 times. So that way
yes,
base
sir.
station will have more probability of receiving it, right?
Yes, yes,
It's like you are sending the same message 2 times.
yes.
In this case, the message is nothing but the preamble. Not only that, also look at my cyclic prefix and also my guard period. So these guard periods are actually inserted to make sure that, okay, I think I have to show you something else. Okay, let me just hold on. I think now we are in the right slide. So look at, okay, I think I should have used this illustration to explain. Okay, let's look at this example where I have two devices, user A and B are device 1 and 2. One is closer, other one is far away from the base station. So this picture is kind of showing you about the timing advance. If I look at, I think it is very obvious that device 2 will have to have more timing advance compared to device 1. So all of you should be agreeing with me. And because device 1 is very close to the base station, and so this is a slot, okay? Let's call it as this is my patch slot. 1 millisecond or whatever it is. It could be, again, as I was mentioning, it can even go beyond 1 millisecond as well. Let me make it as it is just like my patch slot. Now I have these two devices transmitting, or I'm taking these two cases of device 1 transmitting and device 2 transmitting. So by looking at the time at which, so this is at the reception at the base station. This is the case I'm talking about. So now by looking at the preamble 1, which is sent by device 1, so what you can say, what base station can say or kind of estimate about the device 1's location?
It is closer to the base station.
So
Because
even though it doesn't even know the GPS coordinate of the device 1, it kind of estimate that because the preamble 1 has immediately started coming from the beginning of the patch slot. So that way, yes, it comes to know that it is very close and the timing advance is very, very negligible, like could be like few microseconds or something. But as you see, look at the device 2's preamble reception at the base station. So I'm talking these two in two independent cases. I'm not talking the case where both the device 1 and 2 are transmitting. I'm talking two different cases. Case 1 is device 1 is transmitting and its preamble is received at the base station. That is over. Now take a fresh case where I have device 2 which is transmitting its preamble, and in this case I have assigned certain patch slot of whatever the duration, and by looking at this one, look at this one. Now the base station is actually patiently waiting. This is the delta T. So only after the base station has seen elapse of delta T time since the beginning of the patch slot, it has started seeing a preamble getting received at the base station. And what is delta T here?
Time advance.
Yeah, delta is the propagation delay that we can use to adjust the timing at the device 2, so that next time device 2 has to transmit delta T time advance compared to the beginning of the patch slot. But what I wanted to talk about in this slide is not about these 2 points, because already I talked about timing advance earlier. So I'm talking about the guard period that you have here. The guard period that you have here is nothing but the delta T. But I cannot set a different guard period for different devices based on their location, right? So I have to factor in the worst case scenario. So can somebody tell me, when I am designing my patch slot, what should be the maximum value of the guard period that I have to set, so that no matter where the device is, even if it is transmitting at whatever that, from whatever the location, I should able to get its preamble within the patch slot.
So the guard time should be almost the range of the cell edge, the distance
So,
from the cell to the cell edge.
so what you are saying is, okay. What you are saying is the guard period, which is nothing but maximum delta t, right? Right? This is the
Yes,
propagation
yes.
delay from cell edge to G node B, right?
Yes, yes.
So that is what the guard period is about. You are absolutely right on this point of view. So rather than worrying about where the user is there and setting the guard period, so when operators are configuring the base station, they know that, okay, I am now deploying in rural setting or urban setting. They know what is the transfer power, and they know what is the minimum SINR or received power should be received to be able to even to use, let's say, MCS0 or something. So by doing all those calculations, you can know what is your maximum transmission range. Let's say it is 5 kilometers. So 5 kilometers divided by speed of light will give you what is the one-way propagation delay. So that is what set as a guard period here. So can you see this figure? So we have the cyclic prefix followed by your preamble sequence, then followed by the guard period. But look at here, compared to the preamble format 0, I have more guard period in the preamble format 1. So my original question was can you think of a scenario where you recommend to use format 0 versus format 1? It is very clear that format 1 help you to able to very successfully receive the data from the users, or in this case preambles. But do you think of any scenario where format 0 is going to be better?
In case of millimeter wave, because the range is small.
Okay, so you are talking about millimeter wave where, okay, yeah, we can think of that. But anything else? What if it is a small cell or indoor cell?
Yes, there also the range is small.
Yes, yes. So when the range is, see, guard period is a function of the propagation delay. So when I say my cell range is small, I'm also telling that my propagation delay is small. So then I need not have larger guard period, right? That is one thing. And also you can see in the format 0, I'm sending sequence only once, not 2 times. So when do you end up transmitting preamble sequence only once rather than multiple times? In which scenario you end up transmitting sequence only once versus repeating n times? Can you
We
guess?
don't require reliability.
No. I'm talking about the case. Yes, by transmitting multiple times, you are improving the reliability of RACH process. I agree that. I'm talking about other scenario where other case, opposite case. In which scenario you feel that it is redundant to transmit n times, where you want to set n equal to only 1. So if you know for whatever the reason that channel conditions are good and the cell is small, then I can live with the small guard period with only one repetition of preamble sequence, right?
Yes, of course. Yes.
That's what is being shown. And I'll look at other case, very bad case or good case. The format 2 is extremely extreme case where you have very high guard period and you are repeating the preamble sequence 4 times. So this is when the user is at a very disadvantaged location with respect to the base station. Okay. And also look at the preamble duration. It is 4.3 millisecond, even though RACH slot is supposed to be there. But now look at one more case. Here, look at here. Unlike the case where you are seeing here 4 sequences are where n equal to 4 occupying 4.3 millisecond. I'm showing again n equal to 4, but this time I'm showing you only 1 millisecond. Do you know how it is possible? This is a case of shorter preamble. Okay, so rather than using longer preamble of 839 bits, if you use 139 bits, you can able to pack all of them, even if you are retransmitting multiple times within 1 millisecond slot. So then they have defined even additional preamble format like A1, A2, A3, so which are meant for I think FR2, where you can see there you're using only the shorter preambles and they occupy even a fraction of a slot of 14 symbols. That way it is possible for you to pack more than one sequence or one preamble in time domain. Where I was talking about we can have maximum of n preamble in the time domain or maximum of 7 RACH occasions in the time domain. Yeah, so these are all different thing, and so don't get scared away, but this is what the standard is talking about. So how do you configure the patch? Like if you, maybe I'll stop with this one, just bear with me for a couple of more minutes. Okay, I hope you understood about the guard periods and why we need to have them. Okay, so these are about the repetitions, and these are all about long preamble that I said. Okay, look at this configuration. I was just giving a toy example of period of periodicity with 3 RACH slot, where I was showing you about K and T embraces blocks in the frequency domain. So this is a thing I'm showing you. So an example of that is being shown here. You can understand by looking at this case. So what is being shown here is if the base station is configuring, like as part of this, I think SIB1 base station is also informing to the user that what is the patch configuration index that is going to use. So do you know why we need to worry about that? Because after listening to MIB and other thing, you are only synchronized in the downlink, and now you wanted to synchronize in uplink. For that, you have to send preamble in a RACH slot. But as a user equipment, you need to know which are the slots that are configured as RACH slot. In this figure, I'm showing that, okay, I have these 3 slots in a period of whatever, 20 slot or whatever it is, configured as RACH slot. But this information should be conveyed somehow to the user equipment. So in 5G, the way that is being conveyed is by doing hard coding at both the base station side and also at the user equipment side. So each user equipment has this table. So what base station does is, as part of SIB1, it will say that I'm going to use patch configuration index, let's say 0. So by looking at the patch configuration index value in SIB1, your handset will come to know that, okay, these are the slots. Like an example could be something like what you see it here. So look at one of the things that I'm showing, like take in this case, what I'm saying, what you see is that patch configuration index 0 will have preamble format 0. When I say preamble format 0, so the one that I talked about where n equal to 1, where everything is fitting inside 1 millisecond. That is the case. And this is the case where n subframe number mod x equal to y. So in this case, x equal to 16 and y equal to 1. Okay, so basically what it is basically showing is, just to hold on. Like if you look at very carefully, I'm showing so that is what being shown here. So can tell you for what value of this. So this equation is true. So subframe number, as you see in a given frame, how many subframes I will have? Subframe number, right? 0 to 9 only, right?
Yes. But how is it like getting one?
No. So you have to put some value here so that this condition is true. For
So
what
I think
values of
someone is
subframe number, this mod 16 equal to 1?
117.
Only this one only, right?
Yes.
So you got what I'm trying to say? Basically, you are specifying x and y, and this could be 0 to 9. So now we are verifying or basically making sure that for what value of the subframe number, this condition is true. In this case of preamble format 0, so you can transmit your, you can configure pre-patch in subframe number 1 only. That's what you can see here. See, it is being shown that the subframe number is 1 and the starting symbol, like if you take, let's say FR1 with numerology 0, we have only 14 symbols. Basically what I'm saying that I have my patch starting from symbol 0. And these are the cases where I can have how many patch slot within a subframe. And the next one is talking about I can have how many RACH occasions within a RACH slot. So these all are undefined because these are very simplest cases. But if you take one of these case, like when you go for short preambles, like A1, so it is kind of telling that you can use either subframe number 4 or 9 as your patch slot. Okay, and it is starting at 0. Okay, 0 symbol, 0th symbol, and it is showing that you can have one slot within a subframe. Okay, basically in this case it is undefined, but in this case it is defined as 1. And because I'm talking about using a short preamble, I can have multiple RACH occasions within a slot. Okay, so in this case, where is it? Okay, I think I was talking about this. I can have 6 RACH occasions. Because in the time domain, I need not use all the symbols for a given RACH. I can distribute it. And I think the last one is about, yeah, the duration of the thing. The duration of the patch. Okay. So like that, this table is hard-coded in your smartphone or your handset. So when the base station is advertising that, okay, I'm using the configuration index 255, it knows that, okay, the base station, I have 13579 subframes available for me to transmitting my preamble by using that as my patch slots. And it also knows that what are the starting symbols and how many RACH occasions are there and all. Okay, so I think with this background on how we can have multiple RACH occasions and why we need to have guard period and how reputations are going to help when the case of having poor channel conditions. We'll talk about the CBRA, the context-based random access, in bit more detail in the following class, where we'll look at the case where what happens when there are two handsets we're going to transmit with the same preamble. How the contention or the collision can be resolved using message 4 that is transmitted by the base station. So these cases that we'll see in the following class. And looks like now I have to take 2 more classes. I thought I can finish it by Tuesday. So Tuesday maybe I will complete this RACH process. So I think it is taking more time than what I anticipated. Then we'll have one more class on handovers, and we'll look at how handovers also use RACH to be able to reconnect with another base station for seamless handover of the connection. Okay, so if anyone having any further doubts on these concepts, so I can spend some more time, but otherwise, yeah, you can carry on. And I want you